Good morning. I am Bhuvaneshwari. I work in the area of power electronics, electrical machines and drives, and in all the application areas of power electronics, such as power conditioning, power quality, renewable energy systems, electrical machines and their controls, and power supplies as well. I have worked in the area of electrical engineering for the past 3 decades. So I had worked earlier in IIT Delhi for almost 23 years. And after that, I have been working with Mahindra University. So in this particular course, which is consisting of almost 40 lectures, we are going to take a look at what is electric drives, how do we really understand its working principle, how do we control them? How do we implement them? And we are going to look at all basic concepts of electric drives and their control. Okay. So what is an electric drive? What are its applications? Why is it very important to study this kind of a drive? That's what this introductory lecture is going to tell you. Okay. So if you look at a motor, it has an inherent speed torque characteristics. It doesn't have, any variability in terms of its speed torque characteristics. For example, if I am looking at a DC motor drive, separately excited DC motor drive particularly, I would say if I am looking at what is the speed for a given torque, it is actually predetermined. We are going to have this as the separately excited DC motor drive characteristics. If you are looking at no load condition, this is zero torque condition, it is going to have a speed which is omega no load. And if you are looking at a particular torque, when it is delivering a particular torque at a rated voltage, then you are going to see that the speed value is going to be something like this. This is going to be the omega load or omega full load. So the speed is going to vary as the torque demanded from the motor keeps on changing. But of course, this is when we are applying rated voltage and we are essentially giving rated excitation. So when we give rated field excitation and rated voltage, this is going to be a fixed characteristics as far as the DC motor is concerned. On the other hand, if I'm going to look at a three-phase induction motor, again, I can draw what is the speed variation for a particular torque variation in induction motor drive. And I'm going to have the characteristics somewhat like this. This is the way the induction motor characteristics are. I'm sure all of you must have studied about three-phase induction motor. So you can say that this corresponds to synchronous speed, which is decided by the frequency and the number of poles. And as the slip increases, you are going to have the slip increasing, which means the speed is decreasing. The slip is going to increase in this direction. As the slip is increasing, you are going to see that the torque increases. But after certain point, when once the torque reaches maximum torque, we are not really going to have any further increase in the torque at all, even if the slip is increasing. So these are natural characteristics of the motor. So the natural characteristics, if I want to really match that with that of the load requirement, if I want to match the characteristics with that of the load requirement, then how am I going to really control the machine in such a manner that its speed torque characteristics match exactly with that of the load characteristics? So that is essentially done by the drive unit. For example, if I am, looking at an electric vehicle will generally require a very high starting torque because it has to essentially haul the entire weight of the vehicle and the passengers, everybody who is sitting in the car. So that means the torque requirement at the beginning itself is going to be very, very high. So if it is going to be high at zero speed, if I want really a large torque, that means I have to ensure that sufficient amount of electrical energy is imparted to the motor. So my controller or the drive unit has to ensure that sufficient amount of electrical energy is imparted to the motor so that it is able to really start rolling. The wheels are able to start rolling. And especially if you look at the vehicles that are plying on the road, they have to compete with the IC engine based vehicles. Right now, most of the vehicles are still IC engine based vehicles as far as the road is concerned. So the acceleration has to be as high as what we see in an IC engine based vehicle, which means we have to give an acceleration almost from 0 km per hour to 100 km per hour within a matter of 4 to 5 seconds. So that will require a huge amount of torque to be imparted to the electric vehicle motor. So that means the kind of electrical energy supply that I am giving to the motor, which is propelling the electric vehicle, that has to be really, really high. On the other hand, if I'm looking at a fan, when the fan is rotating at a very slow speed, it is going to displace very small amount of air. So the kind of torque requirement at low speeds in a fan motor is going to be really, really small, whereas at high speeds, it's going to be pretty large. So the requirement of torque and speed heavily depends upon what kind of load mechanism I am looking at in any of the drive mechanisms. So the load dictates what kind of torque and what kind of speed requirement my complete system or mechanism wants. So accordingly, my motor has to be driven as per the requirement. Okay. So the main purpose of drive is to ensure that the load characteristics and the characteristics of the motor are matched with each other. So for that, you might have to control the voltage or current or whatever. So all these things are done invariably by power electronic controllers or power processing units. So to understand the drive mechanism, there are mainly two prerequisites. So one of the prerequisite course in this particular case is electromechanical energy conversion systems, that is basic understanding of motors. The second requirement is understanding of power processing units. So the power processing units that we are looking at generally are power converters like AC to AC converters or AC to DC converters or DC to DC converters and DC to AC inverters. So these are the typical power electronic converters that we will be employing in this particular course. So in the next 40 lectures, we are actually going to look at the various mechanisms that are involved in a drive unit and how exactly they are operated, how exactly they are controlled. So that is what we are going to look at in the next 40 lectures. So let me start with the PowerPoint presentation, what I have got here. So if you look at electric drives, basically it is going to consist of a motor and a control mechanism. These are the two things that are going to be put together along with several other auxiliary units which are going to enable implementation of the entire drive unit. Okay. So as I told you, I had worked in IIT Delhi for over 23 years. And currently I am working as a professor of electrical engineering in Mahindra University Hyderabad. And if you have any queries or questions about any of the lectures or any doubts, you can always write to my email address, which I have given here, gohan225@gmail.com. So the outline of my first introductory lecture is going to be somewhat like this. I'll first highlight the difference between a motor and a drive. Then what does a consumer expect from a drive system? What is expected of a drive system? So that's what I'm going to explain next. Then what are all the different types of drives that are existent in the market? So until the power electronics really came to the forefront, how exactly the speed variation and the torque variations were being handled, how people could cater to the needs of different types of loads. So that we will look at when we talk about different types of drives. Then what are all the merits and demerits of an electric drive system? So all is not rosy about the electric drive system. So there are definitely demerits also. So we'll talk about both merits as well as demerits of an electric drive system. And finally, I would give a lecture-wise plan for the electric drives course. And I would also give reference materials that are corresponding to various topics in the drives course. So as I told you earlier, a motor is not going to have any control over its speed torque characteristics. If it is going to have a particular value of voltage applied to it, which is rated voltage, and if it is going to draw rated current, then it will run at a particular speed called rated speed, and it is going to deliver a torque called rated torque. So for example, if I am looking at 220 volts, 10 ampere separately excited DC motor, and I say that its rated speed, the rated speed is going to be 1000 RP. And let us say its armature resistance is something like 1 volt. So I'm going to have essentially 220 volts minus 10 ampere multiplied by 1 volt. This is going to be 210 volts. This is going to be the back EMF, what is available with the motor, right? And normally we can say that back EMF multiplied by current. So this is 210 multiplied by 10 ampere. That is 2.1 kilowatt. This is going to be the output that is available at the shaft. So this is the output power available at the shaft. Assuming that the mechanical losses are negligible, this is going to be the power that is available at the shaft. So this 2100 watts, which is available at the shaft, divided by 1000, that is essentially going to give me what is the torque in Newton meter. I cannot use RPM as such. I have to use the speed in radians per second. So speed in radians per second is about 104.7 radians per second. I'm sure you should know how to convert the RPM into radians per second. So that is basically 2 pi n divided by 60, where n is the speed in RPM. So we are going to have 2 pi multiplied by 1000 divided by 60. That will work out to be 104 radians per second. So I have to write this as 104 radians per second. So I'm going to write this as 104 radians per second. So this will be approximately 20 Newton meter. So we are going to have about 20 Newton meter as the torque. So what I'm trying to get at is if I apply 220 volts voltage to the separately excited DC motor at rated excitation, and if the machine is drawing a current of 10 ampere, then it would be developing a torque of 20 Newton meter and simultaneously running at a speed of 1000 RPM. So this essentially indicates that the operating point of the DC motor is fixed as long as the voltage and current are fixed. I cannot vary that at all. So if I want a torque of only 10 Newton meter, this is 20 Newton meter, whereas if I want only 10 Newton meter, as a rule, it will run at a slightly higher speed than 1000 RPM. This is corresponding to 1000 RPM. So I would not be able to vary the speed. If I want 10 Newton meter, then the speed is set in stone. I will not be able to vary the speed. So I don't have any control over the speed and torque simultaneously if I am running this motor without a control unit. The control unit is generally called the drive unit. So if I'm not going to have any control unit at all, then we are going to have the speed and torque already set in stone. So there is absolutely no controllability as far as the motor is concerned, because I'm going to run it always at rated voltage, and depending upon what is the torque demand, the speed will vary accordingly. Okay. Whereas if I want controllability, where I would like to match the needs of the load with that of motor, then I will need a drive unit. The drive unit is the control unit. The moment you include a controllability in your entire system, then the system is going to definitely get more complex. It will not be as simple as a simple motor, but the moment you call it a motor drive, there has to be controllability, so it is going to become more complex. And whenever we are talking about a motor, we will be in a position to start, we will be in a position to brake, we will be able to run it. But we may not be able to control the starting, how quickly you want to accelerate the motor, how quickly you want to stop the motor, which is known as braking, controlled braking, and the control of speed and torque. All these things are not going to be possible. Whereas in a drive unit, motor along with the control unit, when you install, you will be able to control the starting, braking, as well as you would be able to control the speed, torque, characteristics of the drive itself as per the requirement from the load side. So if you look at the drive system, it has all these parts. The first and foremost thing is the source. The source could be a single phase AC source, which is normally 230 volts, 50 hertz as far as India is concerned, or it could be a three-phase 50 hertz source, which could be anywhere between 400 to about 440 volts as far as India is concerned, and in 50 hertz condition. So this is either a DC or AC source. AC source could be a single phase or three-phase AC, which is available from the grid. So these values are set in stone. These cannot be changed. Now, if I want the motor to get maybe 110 volts DC or 220 volts AC, or some other variable frequency, variable magnitude AC, in that case, I will need a power electronic converter sitting in between. So I will have a power processing unit which is sitting in between the source and the motor. The power processing unit could be a simple rheostat also, because the rheostat can drop part of the voltage. You guys all must have seen fan regulators at home. Many of the fan regulators are simple resistances which drop part of the voltage and which apply only rest of the voltage to the actual machine. So if I am Talking about the resistance. So this is the resistance, and I'm going to have a single phase source here. And I'm going to apply this with the help of this variable point to my fan. So this is the fan mode. Okay. So if I am dropping a good amount of voltage in this portion, then I am essentially looking at only part of the voltage being applied to the fan. So obviously it is going to run at a lower speed. Whereas if I am going to apply the entire amount of voltage into the fan, which means I'm going to just connect it here. If I connect it here rather than here, then the entire voltage is connected to the fan. Then in which case I'm going to have actually the fan running at full speed. So when you look at the regulator that is available in your home, the regulator essentially does the job of this resistance. Either it drops part of the voltage or it is going to have the entire voltage applied to the fan. So either way is possible. Okay. So the power processing unit could be a simple rheostat, or it could be a power electronic converter, which will convert AC to DC or DC to DC or DC to AC and so on. Different kinds of conversions are possible using power electronic converters. So the power processing unit could be receiving a control signal from the control unit, and the control unit will be giving a control signal depending upon what is the kind of error I have either in the speed or torque or current or voltage. So what happens is the power converter sends the voltage and current to the motor, and the motor now converts that electrical energy into mechanical energy. The mechanical energy is manifested in the form of speed and torque. Now, there will be a coupling mechanism or conversion mechanism that is existing between the motor and the load. The load could be something like a translational motion load. So if it is it's something like a conveyor belt, which is there in the airport. Okay, so it could be carrying luggages in a conveyor belt mechanism, which is actually requiring a translational motion, whereas many of the motors only impart rotational motion. So this conversion mechanism could be rotational motion to translational motion converter, or it could be having a gear mechanism which might convert from high speed to low speed or low speed to high speed. For example, electric vehicles, most of them might require a little lower speed, whereas the motor itself might rotate at a high speed. So we may have a reduction gear. The speed might actually be reduced from a higher value to lower value so that the electric vehicle's wheels are rotating at a lower speed, but the torque will be increased. So this particular mechanism, whatever the conversion mechanism that we are talking about, this could be translation to rotation converter or rotation to translational converter or gear mechanism, in which case the torque and speed both will be converted to appropriate level. So both may be converted to appropriate level. So this is the conversion mechanism which is sitting in between the motor and the load. Now, when the power electronic converter is giving the voltage and current to the motor, those may be sensed so that they will be fed back to the control unit, and the control unit will be adjusting the control signal that is given to the power processor such that the reference and the actual quantities are not differing from each other. They are exactly same as each other. For example, I may be wanting to run the motor at 1500 RPM and I may be starting from rest. So at rest condition, the speed is only 0 RPM. Voltage we have applied, but the motor may not be drawing any current. Now the power processor will pump the current to the motor. Because the current goes into the motor will develop a torque. So the motor will start rotating. Now, as the motor rotates, the speed that is being sensed, that will slowly change. So that speed will be compared with the reference speed of 1500 RPM, and correspondingly the control unit will decide whether the current has to be increased further or it should be maintained at the same value or decreased further. So the power processor is going to adjust the electrical quantities accordingly, which is being pumped into the motor, such that the reference speed eventually is followed by the actual speed. So the actual speed also becomes 1500 RPM. So here, if you look at this, the solid line indicates that we are directly sensing an electrical quantity and giving it to the feedback mechanism so that it is eventually sent to the control unit. Whereas if you look at these two dotted lines, they indicate that one of them could be speed, the other one could be torque. They are mechanical quantities. So these mechanical quantities have to be converted into appropriate electrical quantities using transducer mechanism. So when we talk about the feedback, this can include transducers. Whereas here we may have current and voltage sensors. We may have current and voltage sensors here, whereas transducers may be sitting here. Transducers essentially convert mechanical quantities into electrical quantities so that it can be directly passed on to the control unit. Another thing is the feedback mechanism might also have something called signal conditioning circuits. So signal conditioning circuits are basically those circuits which can actually convert the signals that are obtained from the transducer from one level of voltage or current to another level of voltage and current. Typically, a signal conditioning circuit could be an amplifier. So if I'm getting only milliamperes of current, but I want the current to be of the order of amperes, then I can use amplifier. Similarly, if I am getting only millivolts of signal and I want this to be a few volts, then an amplifier could be in a position to do this. So amplifier could be one of the signal conditioning circuits. Sometimes there could be level shifter. So if I am looking at a voltage, which is something like an alternating voltage. So what I'm getting from a transducer is something like this. I am having plus 2.5 volts to minus 2.5 volts. This is the kind of alternating quantity I am getting from my transducer. But most of the times, what I see as the control unit may be a computer, digital electronic circuit or analog electronic circuit. And this may be able to handle only a unipolar signal. What we mean by unipolar signal is it may be able to handle only positive voltages, DC voltages. It will not be able to handle the negative voltage. But I have to pass this transducer signal to the ADC. But the ADC is a unipolar ADC. Analog to digital converter is a unipolar ADC. So in which case, I might try to add another 2.5 volts to this particular signal. So in which case, this entire signal will be modified in such a way that I am going to have basically it will start from, instead of 0, it will start from 2.5 and it is going to come to 0 and then go like this. So the maximum value of voltage will be now 5 volts. This will be 2.5 volts. And what was minus 2.5 earlier will be 0 volt. So this voltage has not lost its shape. but it has been shifted by 2.5 volts. So instead of minus 2.5 to plus 2.5 variation, now the voltage variation is from 0 to 5 volts. Okay, so signal conditioning circuit can be adder circuit, subtractor circuit, it could be a multiplier circuit, it could be an amplifier circuit. One of those things could be the kind of signal conditioning circuit you may have. So the feedback circuit need not be a simple buffer, which will simply pass on from the voltage sensor or current sensor directly to the control unit. Rather than that, it can have transducers, it can have sensors, it can have amplifiers, it can have signal conditioning circuits, and so on. Now, the control unit essentially gets the difference between reference speed and the actual speed, what we get from the feedback mechanism, or reference torque and the actual torque, or you may get the difference between, it will calculate the difference between reference current and the actual current, or reference voltage and the actual voltage. And this error, what is there as error signal, which is the difference between the reference and actual values, that will decide whether the actual voltage applied to the motor needs to be increased, decreased, what needs to be done. That will be decided by the control unit. So the control algorithm should be sitting inside this control unit. So it could be an analog electronic circuit, digital electronic circuit, or it could be a computer or a processor which would have the algorithm written down already. So correspondingly, the power processor will get a triggering or firing signal. So this is going to get a trigger signal. So this is going to get a trigger, and that trigger is going to alter the way the voltage and current are applied to this particular motor, so that the motor develops the torque and speed in such a manner that the load will be exactly getting the amount of torque and speed it requires. That is, the load requirement will be matched with that of what is developed by the motor as such in the form of speed and torque. So the drive system, the heart of the drive system are mainly the control unit and the power processing unit. And of course, without the feedback mechanism, the control unit will not be able to function. So all of them are extremely important. The feedback mechanism is something like a limb. So, you would not be able to really pass on the actual output of the motor or the entire drive system unless we have the feedback mechanism itself put in place. So what is expected of a drive system? So a drive system generally should have easily controllable torque and speed. So that if the torque and speed are easily controllable, that means we would be able to match the requirement of the load with that of exactly the motor. Whatever is the motor developing as torque and speed, it should be exactly matching with the requirement of the load. Only then there will be equilibrium between the motor or the drive system and the load itself. If the two are not matched with each other, there will be continuously oscillations in the speed and torque. So if that needs to be avoided, the drive system should control the torque and speed imparting capability of the motor very, very accurately. And another thing is just the accurate control is not sufficient. It should also control the speed and torque in a very, very fast manner. For example, if I'm talking about an electric vehicle, if I see a red light, if the driver sees a red light, immediately the driver should be able to stop the car. So which means the response has to be really, really fast. You cannot overshoot the zebra line and stop way beyond the zebra line or way beyond the intersection. So it's extremely important that fast response is, one of the major traits of the drive system. Another thing is, if on the road you see suddenly a pedestrian crossing, then immediately to avoid the accident, you have to ensure that the vehicle is stopped. So again, fast response is key to averting any mishaps or accidents in an electric vehicle. So fast and accurate response is extremely important. And another thing is the drive system should be sensitive to whatever inputs the driver is giving. So let us say we are just going past one of the shops and we want to just stop right in front of the shop. So in which case the driver will give an input signal saying that the speed has to be brought down to 0 right away. So continuously the drive system should be checking for inputs from the driver, and it should be sensitive to the inputs from the driver, and it should immediately respond to the needs of the driver. Otherwise, the entire interface between the driver and the drive system has to be really, really sensitive and responsive. Otherwise, it's not going to really work well. Another thing is, in some of the mechanisms, it will not be only speed control and torque control. Sometimes position control becomes extremely important. For example, if I'm talking about a microscope, where probably we are looking at a particular slide under the microscope's lens has to be adjusted exactly at an accurate position for me to look at the slide properly. And especially if it is automatic imaging that is being done, then the microscope's lens adjustment will also be automated, and the image will be captured probably in a computer, in which case the position of the lens becomes extremely important to obtain good images. The same way, if you look at a telescope, when we are looking at astronomical bodies, then, again, the telescope's lens have to be adjusted properly so that we are able to look at the astronomical bodies. Maybe it is a star, maybe it is something like a satellite. So we would be able to look at that very, very clearly. So in many of the cases, position control becomes very important. Another typical example is robotic mechanisms. An arm has to be probably moved by 4 centimeters, or it has to be rotated by a few millimeters. So in those cases also, position control is extremely important. Pick and place robo, or lathe kind of mechanism where you are going to do thread cutting, or you're going to do taper turning or turning. In all those things, position control becomes important. So not only speed control and torque control, but even position control becomes extremely important, and all of them should be implementable with the help of a drive system. So all along I had been talking about speed and torque just to emphasize the fact that position control also becomes extremely important. I'm just adding that these are mainly the 3 kinds of control mechanisms that are implemented. And of course, speed control or torque control is normally implemented with voltage control or current control. So it goes without saying that the stimulus in a motor is voltage or current. So those have to be adjusted to obtain appropriate amount of speed and torque, and hence move the mechanism in such a way that correct position is occupied by a particular load. So these are all very important. Unless we are able to implement any of these control mechanisms, your drive becomes really useless. There are different types of drives that are available in the market. Very commonly available is mechanical drive. You see them in the form of cars. All of them are driven by IC engines, maybe diesel engine or petrol engine. So compression ignition and spark ignition engines. So mechanical drives are available all over. Major disadvantage of the mechanical drive is its pollution. So the kind of carbon dioxide emission, carcinogens, all those things, they are well known. The harm done by them are well known. So IC engines are one of the drives that are available. They are quite easily controllable, but definitely not as accurately controllable as what electric drives could be. So mechanical drives are very commonly available. Another type of drive that is commonly employed is hydraulic drive. The hydraulic drive mechanism typically is in the form of either steam engine or wind turbine, and hydro turbines that are used in hydropower stations. All of them are hydraulic drives. Hydraulic drives, again, one of the problems could be the leakage of steam or some kind of leakage of water from the water wheels. It's definitely, it cannot be tolerated. So that is the reason why we use a lot of gaskets and rubber linings and things like that. So if there is even a slight leakage, there could be mishap. The entire mechanism could become very messy. So that is the reason why, although hydraulic mechanisms are available at extremely large ratings, the mess associated with that, the dangers associated with hydraulic drives, these are some of the problems. So if they could be replaced by electric drives, that would be wonderful. Pneumatic drives are another type of mechanism where compressed air or compressed gas may be utilized, and when it is expanding, it is actually trying to drive a mechanism. So it is like a loaded spring. So when you have a spring which is loaded, when you allow it to slowly unwind, it drives a mechanism like olden days alarm clock. So it is very similar to that. The pneumatic controlled drives are basically operating with compressed air. So again, leakage could be an issue in this particular case because you are holding air at a very high pressure. So it's not going to be easy. So the fourth type of drive which have come into existence since 1960s and 70s, that is electric drives. These electric drives have really become state-of-the-art kind of drive mechanism lately due to the advent of power electronic converters. So compared to different types of drives like pneumatic or hydraulic drives or IC engine based drives, what are the advantages of electric drives? If a thermal power station is shut down for a few days, which is actually driven by steam, right? The turbines are driven by steam. So if you want to turn on or put into service a thermal power station from its off situation, it will require anywhere between 12 to 15 hours minimum, because you have to first make sure that the boiler is, functional. The fuel is, burning in the boiler. Then water is converted into steam, and the steam becomes high pressure, high temperature, super saturated steam. And then it drives the turbine, and the turbine actually drives the generator, and the generator is able to really generate electricity. So all these things will take quite a number of hours before really the power station starts functioning. So the warm-up time in the case of a steam turbine kind of a system is almost 12 to 14 hours. Whereas in an electric drive, all you do is turn on the switch and it will start running. So there is no warm-up time involved in an electric drive. Second thing is, the electricity does not really give any emission except for the losses in an electrical machine. The losses in an electrical machine is only of the order of 10% or 5%, nothing more than that. Whereas if you look at the thermal power station efficiency, the total efficiency is only of the order of 70% or less than that. And if you look at the efficiency of IC engine based drives, the efficiency is only of the order of 15 to 25%. So compared to the amount of emissions and the kind of efficiency you get in different kinds of drives. Electric drive is pollution free. It doesn't really give any emission of carbon dioxide and other gases. And the efficiency is much better than many of the other kinds of drives like IC engines or steam turbines and so on. Speed and torque are very easily controllable. So we would be able to match the characteristics of the load and the electric drive exactly so that we don't have any spillover. We don't have any oscillation in terms of speed and torque. And if you want to overload the drive, that is possible in an electric drive. What do we mean by overload? So let us say my load requirement is somewhat like this. For some time, it is going to require 200% of normal or average capacity. For some time, it is going to require only 80% of normal capacity, and that is for a longish duration. Then it might require something like 120% of normal capacity. So this is going to be the kind of load requirement. So this is T full load. Compared to T full load, how much is the requirement from the motor drive? So this is the load requirement. So load torque requirement. So in this particular case, should we employ a motor which is giving you 200% full load torque or 80% full load torque or 120% full load torque? So if we employ a drive which can probably give 100% full load torque, for a short while I may be able to load it for 200%. Again, for a short while I may be able to load it for 120%. These are generally known as overloading. So how much is the overload capability of a motor without getting overworked or burnt? If I load it to 200% and if the motor is completely burnt, then it is of no use. So how are we going to really assess the overload capability of the machine? We look at it eventually. But in general, electric motors, many of them are capable of delivering anywhere between 200 to 250% of its normal torque. So the overload capability of many of the electric machines are pretty good. Like I told you earlier, there is no mess. Defense, there is no leakage of oil or air or steam or something like that. So generally, we are not going to have any hazardous situation with electric motors. That is one of the major advantages. And with the kind of transmission of electricity available all over the country now, we should be able to operate an electric motor anywhere. Wherever there is a power outlet in the form of a plug point, we should be able to operate a motor. And 4-quadrant operation of an electric motor, it is easy to achieve. What we mean by 4-quadrant operation of an electric motor. So if I say that the speed is positive in this direction, that means the speed is negative in this direction. And speed is increasing in this direction. Whereas if I talk about torque, torque is positive here, whereas torque is going to be negative in this direction. So if I am talking about, for example, a lift which is going against the gravity, it is lift going up. When it is going up, then the motor has to propel the cage upwards, and simultaneously the torque also has to be positive so that the cage is propelled upward. Whereas if I want to come down, we may be actually coming down like this. The speed is in the reverse direction, but if the gravity is pulling it, we have to ensure that the lift cage is not coming and dashing on on the floor. So to avoid that, we might have to actually generate a torque which is opposing the motion in the downward direction. So we may have to generate a torque which is positive, which will try to push it upwards, but the gravity is pulling it downwards, but it will come in a controlled manner because this torque is going to deter this particular cage from moving very fast in the downward direction. So we might have to have the operating point either here or here or here or here. So all four quadrants of operation may be required. So for example, even in an electric vehicle, I may like to reverse for some time. Or if I'm going up the hill or down the hill, accordingly, I might have to generate a torque in the positive direction or negative direction. So four quadrant operation becomes extremely important in any of the drive system. And in an electric drive, it's very, very easy to achieve four quadrant operation. We will look at four quadrant operation in a greater detail in one of the forthcoming lectures. Generally, the electric drives are not available at extremely large rating. The maximum capacity of an induction motor is only to the tune of 2 megawatt or 3 megawatt. Whereas if you look at the steam turbine, they are available up to hundreds of megawatts. So one of the major disadvantages of an electric drive is it is available at only limited rating. The second one is if we talk about an electric vehicle, generally it is powered from battery. And currently the battery size is the limiting factor for the electric vehicle's range. The two-wheeler can travel at the most only 50 kilometers or 45 kilometers in one go. That is because the battery that is actually sitting within the two-wheeler, it will be able to propel that motor only to the tune of 40 to 50 kilometers, nothing more than that. So battery is one of the major limiting factors. The energy storage system, what is available as of today, is the limiting factor for any electric propulsion system. So in general, if a battery is powering an electric drive, it's going to be extremely difficult to have a long range vehicle. So here I'm trying to give you the lecture wise plan. So the introduction will go on for 1 more hour. So about 2 hours I'm going to spend on introducing electric drive scheme. Then I'll be talking about different kinds of load systems, something like a lift or a fan or something like an electric vehicle. So different types of loads and how they behave, how their speed torque characteristics vary. So all these things have to be talked about so that we know exactly how we need to control our electric motor as per the requirement of load. So we'll be talking about different types of load systems as well as conversion mechanisms, how translational to rotational or rotational to translational conversion mechanisms work. And using those mechanisms, how do we really arrive at what kind of rating of the motor we require? All those things will be decided based on what we discuss in dynamics of load system. Then we would be talking about speed sensing, current sensing, voltage sensing, torque sensing, all those things we'll be talking about in sensing mechanisms and what kind of control mechanisms are adopted for controlling the speed or torque or position. So whether it is P controller, PI controller, PID controller, whether it will be digital controller, analog controller, what all different types of controllers are available. We'll be talking about those in topic number 3. And that will span about 1.5 hours. Then once we know what kind of losses take place within the motor and drive system, that losses, those heat losses are going to heat up the motor. So they can actually affect the insulation. They can make them melt. So we would be talking about what all losses take place in the motor, how exactly temperature-wise calculations can be done in a motor drive mechanism. Based on that, how are we going to choose the rating of a particular motor for a given load duty cycle? So if a load is going to have 100% power all the time, then there is no problem. You can just select a motor which is corresponding to that 100% power. Rather than that, if the load is going to fluctuate on a continuous basis, how are we going to really adjust that control mechanism? And how are we going to choose a particular motor of particular rating? So those things will be talked about in topic number 4. After that, we will be really coming into the meat of the topic, which is corresponding to the DC motor drive, three-phase induction motor drive, and synchronous motor drive. So the DC motor drive, we will talk about both separately excited shunt and separately excited and shunt motor are almost going to behave the same way. But we will also talk about series motor drive. In all the DC motor drive mechanisms, we'll be talking about what kind of starting mechanisms normally we employ, how braking is implemented in a DC motor drive mechanism, and how the speed control is implemented in a DC motor drive mechanism. And the speed control can be done either using AC-DC converter, single phase or three phase, if we assume that the power is coming from the grid. On the other hand, if it is going to be a battery-driven DC motor drive, then we have to use a DC to DC converter, which is like a chopper. So how the chopper is going to work about this, and as well as how the chopper is going to go hand in hand with the DC motor, how the characteristics will be modified. These will be discussed in topic number 5. In topic number 6, primarily we are going to concentrate on induction motor drive. So the induction motor drive can be classified as cage induction motor and wound rotor induction motor. So we would be primarily concentrating on cage induction motor, but we'll be just devoting very little time on rotor side control in a wound rotor induction motor. But in stator side control, we are going to concentrate on voltage control, voltage and frequency control. And when we use voltage and frequency control mechanism, it can be either using voltage source inverter or current source inverter. And it could be scalar control or vector control. Vector control is also known as field oriented control, which is FOC, or it could be direct torque control. So we will be looking at all 3 types of mechanisms when we are talking about voltage and frequency control. Even in 3-phase induction motor drive, we will be looking at starting, braking, and speed control mechanisms for a 3-phase induction motor drive. And in synchronous motor drive, specifically, we are going to look at 2 types of speed control mechanisms. One is true synchronous mode, where voltage and frequency can be varied as an independent variable. Whereas in self-control mode, where the voltage and frequency will be varied as per the rotor speed. So the rotor speed will be sensed, and accordingly voltage and frequency will be varied incrementally. So self-control mode has the major advantage that no oscillation will be seen generally in the working of self-controlled synchronous motor drive. Finally, if time permits, we are going to look at special machines like permanent magnet brushless DC motor, stepper motors, as well as switch reluctance motor. So we will try to devote about 3 hours in special machines and their control. So throughout this course, I'll be mainly following the book by Professor G.K. Dubey, Fundamentals of Electric Drives. But this particular book does not have the topics related to the field-oriented control as well as vector control as well as direct torque control. So I may be looking at for those two topics, the book by Murphy and Turnbull that gives field-oriented control extremely well. But there are other books by other professors, like S.B. Devan has written a book on power semiconductor drives, which is from John Wiley. This is also extremely well written book. It covers both AC as well as DC drives, but it does not cover again vector control and direct arc control. There is one more book by Professor G.K. Dubey, which is called Power Semiconductor Control Drives. This is from Prentice Hall International. This again covers all the drives extremely well, but again, this does not have vector control and direct arc control. Please note that JMD Murphy and FG Turnbull's book does not have DC motors covered under its title. Only AC motors are covered in this particular book. There are many other books that are available. These two books, that is N.K. Day and P.K. Sen's book, as well as S.K. Pillai's book, they have large number of problems worked out. So it will be quite useful for understanding the concept of electric drives. There are again two books that are written by Professor Peter Vaas and Professor R. Krishnan. Both these books give a lot of conceptual ideas about vector control and direct arc control. And this electric motor drives by R. Krishnan also gives a lot of modeling and simulation aspects of drive system. Apart from that, I also would recommend Professor Neg Mohan's book. There are two books written by him. So there is one book on electric drives, an integrative approach. That is one of the books. There is another book called Advanced Electric Drives. Both these books are extremely well written. Many simulation problems are given in those books based on Simulink MATLAB. So I would strongly recommend that you can read those books as well. So this is all I had for lecture number 1. So we would be starting to look at the general aspects of drives in lecture number 2. So I'll continue with the introduction and I'll be giving you general aspects of drives in lecture number 2. Okay. So until then, if you have any questions, you can again write to me in my email.